Today we're going to start another application of reaction prediction by looking at reactions where we predict whether or not a solid is going to be made. In order to do this, we have to do two things. Number one, we have to talk about solubility again. This is a topic that we really haven't discussed since you learned about it in grade 7. Then we need to do some solubility predictions using a new table that you are going to get today. And then we can look at doing what's called a net ionic equation, which is a prediction of whether or not a precipitate or a solid will form in a chemical reaction. So if you can remember all the way back to Science 7, too far away, hey? That was the year that you built thermometers from scratch. Ah, okay, that brings back some memories. All right, and you also played a lot with mixing sugar with water or Kool-Aid with water, and you did different things to the water or the sugar cube to try to dissolve it really fast. It was called the Great Disappearing Sugar Race. No? Okay. Solubility is the ability to dissolve. What does it mean to dissolve?
Mix into the liquid.
Okay, so a solution is actually a mixture. When you have a mixture that is a solution, can you see the bits and pieces that went into that? No. So dissolving looks like it's disappearing. For example, if you make a saltwater solution to gargle for a sore throat, it looks like the salt is disappearing. But you know if you drink that glass of water, it's going to taste salty. There are at least two things that go in to make a solution. One is the solute, and one is the solvent. If I have something like a sugar cube here and a glass of water here, which one is the solute and which one is the solvent? James? Okay, so the solvent is the dissolver. If you have troubles telling the difference between a solute and a solvent, think about what you have more of. If I'm dissolving salt into water, do I have more water or do I have more salt?
More water.
Much more water. That makes it the dissolver. The solution is the mixture that is made when you combine the two together. Is anybody wearing some jewelry today? Anybody got some gold or some silver on? When we make a gold ring, is it 100% gold? No. Why not? It's really, really soft. You can actually take your fingernail and start scratching the gold band if it's 100% gold. We mix that gold with something to give it strength. Otherwise, anytime you did something with your ring on, you would start deforming your ring to the extent that it might not look very much like a ring after a couple of days. Solutions don't have to be liquids. Bronze, gold, sterling silver are all mixtures which are in a solid phase. You can also have solutions which are in a gas phase. Are you breathing in pure oxygen right now? No. Only about 21% oxygen, actually. 78% of what you're inhaling? Nitrogen. You also have some carbon dioxide and some other things that are in the air as well. one of the terms that I have seen a lot on Lab 1.1 is the word dissolving to describe what's going on with the magnesium. This is an incorrect term to describe what happened to the magnesium in Lab 1.1. What is the difference between something dissolving and something reacting?
If it's dissolving, then it disappears.
Versus if it's reacting?
If it's reacting, like you can still see it, but there could be stuff around it.
So, if we were to dissolve salt into water, the salt does disappear, but is it still there? It's definitely still there. When the magnesium reacts, is it still magnesium? No. So when something reacts, it is transformed into something new. In this case, the magnesium reacted with HCl and it formed magnesium chloride and hydrogen gas. This is a lot different than what this is. Magnesium by itself is a metal. Magnesium in magnesium chloride is actually now an ion. It's Mg2 positive, which is chemically very different than Mg. When you dissolve something, it becomes part of a mixture. That means that it's still there. If it's still there, how come we can't see it? Yes, way too small. I'm going to just change to a video here. What this is going to do is zoom into the particles which make up salt and water to show you what's happening to the salt crystal on a microscopic level. Thank you. This has sound, maybe it doesn't. On the right-hand side, the purple and yellow blob is the salt crystal. It is made up of sodium ions, which are represented by the purple circle, and the chloride ions, which are represented by the yellow. Over here, the thing that looks like mini Mickey Mouses is the water molecule. The water molecule has different charge sides. It has a slightly positive and a slightly negative side. Salt is made up of the sodium ion, which is one positive, and the chloride ion, which is one negative. What do you think is going to happen when the water gets close to the salt crystal? Yes, why? You're right, it's going to be attracted. Why is it going to be attracted? Okay, let's think back to Science 9 when we talked about the law of charges. What happens when I get a positive next to a positive? They repel. Negative next to a negative? Repel, but if I get a positive next to a negative, they attract. And the same thing is going to happen here. We have one molecule that has a positive and negative side. We have a second which has a slightly positive and slightly negative side. Opposites attract. So what we see here is that the water molecules are being attracted to the salt crystal, and they're actually pulling off ions. We can see this, because we have so many sodium and chloride ions together in a small space, it's easier to see. Many of you have been on an airplane. I know you've just been very recently on an airplane. When you're way up there, can you see a singular car very easily? It's pretty hard, but you can tell when you're flying over a parking lot. You have many cars together, and it's much easier to see. So as the water particles are attracted to the salt crystal, they start pulling off singular ions. That's what the solution looks like. The sodium and the chloride ions are no longer stuck together. They're distributed throughout the solution. They're still there. But now, because they've been pulled apart, it's too hard to see them. So in a dissolving reaction, it's still there. If it's a chemical reaction, it's totally transformed into a new thing. So when we mix something, how can we tell just by looking at it, or perhaps feeling it, that it is a chemical reaction, or if it's a dissolving equation? How do I know if it's a chemical reaction or if it's a dissolving? What could you look for?
Such as magnesium and bubbles.
Yes. Bubbles means gas. Okay. So we can look for indicators of chemical change. So a gas is being formed. What else could we look for? Yes, we could feel the side of the test tube. Many of you didn't do this. So many of you noted in lab 1.1 that there are gas bubbles. But if you would have felt the test tube, you would have felt a very warm test tube indicating that the temperature is changing. Did anybody do any wafting? This one doesn't have much of an odor change, and I would prefer actually you didn't smell anything that was acidic or basic because it's corrosive, and it will burn the inside of your nose passage. We can look for new products, such as a new color was formed that was not there. Think about when you added the universal indicator to acid and all of a sudden you get the red color. That's because there was a chemical reaction of the universal indicator. If it wasn't red before you put it, it was kind of a browny color. Or when you put it into the base, it turned blue. That's a chemical reaction. If it is a dissolving equation, nothing really changes. It looks like it disappears. If you dissolve something that's brown, it's probably going to turn the solution brown. For example, does anybody mix fertilizer with water? The fertilizer that you use is usually a blue color. Kind of see this side of this bag here is all blue from the Miracle-Gro. It's kind of sticky here that you mix with water. So you would expect the water to go blue because the Miracle-Gro itself is blue. Sometimes the heat changes when you dissolve something. Sometimes it's too little to be detected, but if you dissolve something like ammonium chloride, it will get very cold. Or if you dissolve something like sodium hydroxide into water, it gets very hot. Yes, please. Thank you. I am going to give you a new table. Feel free to put this in the same plastic sleeve, unless you're a rebel. And like you like your tables all over the place. Okay. This is called a solubility table. How was the game yesterday?
Not good.
Did you get a second attempt, or is that it?
No, we get to
Okay. Do you know when yet?
Sunday at 9.
Okay. It says solubility, which is the ability to dissolve, of ionic compounds only. This is not a table that you would use for molecular compounds. In aqueous solutions, what does the word aqueous mean? Nope. It indicates a mixture with aqua, water. So it means that this compound has been added to water. Why do you think it specifies a temperature for this table? Any guesses? Does anybody make homemade iced tea? Why do you make it hot and then cool it rather than make the iced tea cold to begin with? So if you heat up the water, put the tea bags in and dissolve the sugar, you can dissolve more sugar when the water is warmer than if the water is cooler. Then once you've made the tea, you can cool that down and it will taste sweet enough for you. If you make homemade black tea and you don't put in any sugar, it's really, really bitter. And just so if you know, if you go down to the US and you ask for iced tea, it's really iced tea. Like tea. It's not what we have here. So temperature makes a difference because temperature influences how much stuff can dissolve. We have 3 rows. Across the top row, we have mainly negative ions. In an ionic compound, where do negative ions usually hang out? So if I have something like this, CaCl2, this is the anion or the negative ion. So usually it's on the back side. So I start by looking up that along the top row. And it fits right here because this is where Cl negative is. Then I have 2 rows to choose from. I have solubility greater than or equal to 0.1 moles per liter. La 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 la. What's important is right here. It's very soluble, which means that when you write out the compound formula, it gets the AQ behind as a symbol. It says most. That's not really helpful. What does most mean? Basically, anything that's not in the list of ions in the second row. Anytime you have a most category, you always have to check out the second row and see if it's somewhere in here. So if you look there, do you see calcium down there? Oh, it's right here. What that means is if I take calcium chloride and I put it into water at 25 degrees Celsius, oh my goodness. Must be in the right column. And this happens to teachers too, right? Of course, I have to be recording this as well. Calcium is not in this list of 4, which means that it is soluble. So if I have to dissolve this into water, it's going to dissolve. And I would indicate that by writing the AQ behind in brackets. It has a lot of different polyatomic ions in here. Every once in a while, you'll see this. Group 1. What is group 1? Where? Is it grouped this way, or is it grouped this way? Okay. Group 1. Groups go down. Yep. Good job. Okay. So if it says group 1, it means hydrogen, lithium, sodium, potassium, rubidium, cesium, or francium. It does this in a couple places. In these 3, but also it appears up here. Every once in a while, you're going to get this NH4 positive that appears. What in the world is NH4 positive? Ammonium. Remember, it is the only positive polyatomic ion that we're going to be dealing with in Physical Science 20. I am going to give you some practice questions. I'm just going to pop. I've just given you a worksheet titled Predicting Solubility of Ionic Compounds. The first compound on this worksheet is ammonium chloride. The first thing you need to do is write down the chemical formula for ammonium chloride. Chemical formula for ammonium chloride is NH4Cl. Next thing you have to do is look up the anion on the table. Ammonium chloride ends in Cl. So you look across the table. Here is Cl. You come down. You've got a most category here. You've got Cu, Ag, Pb, and Tl down here. None of these is ammonium. Therefore, it fits into this group, which means that if you mix it with water, it will dissolve very well. And it gets the AQ symbol beside it. For ammonium chloride, there's another way to find out whether or not it's soluble. Because anything with NH4 positive is soluble. This is why we have to be really careful about disposing of this substance. We don't want to be sending a lot of this down the sink because it will increase the solubility of different substances like nitrates and phosphates, which can encourage plant growth in ponds and lakes and lead to eutrophication. Try the next one. Iron 3 nitrate. Your first job is to write the formula. formula for iron 3 nitrate is Fe bracket NO3 bracket 3. We start with the negative ion. The negative ion is nitrate, and it fits right up here. We come down, we have this most category, which means we have to check up the other one. Iron 3 does not occur anywhere else here. If I mix iron 3 nitrate with water, it's going to dissolve very well. So I'm going to put the AQ symbol behind it. Just a brief note, watch out because sometimes a metal has more than one ion. For example, iron can be 2 positive or 3 positive. Make sure you check the charge. So for example, if you have lead 2 sulfate versus lead 4 sulfate, one is soluble and one is not soluble because there's 2 different charges and charge makes a difference. So please complete the next 10 questions on the worksheet. So question number 6, sodium hydrogen carbonate. The formula for this is NaHCO3. If I look for HCO3 along the top row here, I'm not going to find it. But there is another way to figure out if this is soluble. What group is sodium in on the periodic table? It's group 1, which fits into this row up here. All group 1 ions. We're going to create soluble solutions. So you actually might want to take out your highlighter and highlight group 1 and NH4 positive because it's the only time when the positive ions are going to be found in that top row.